In this video, we're going to talk about maximums and minimums. So there are two types, so-called absolute maximums and minimums and local maximums and minimums. So let's just dive right in. Let f be a function on an interval I, and let a be any point in I. So if you're not familiar with this symbol, it just means that this is some number in the interval. We say that f of a is the absolute minimum if it's the smallest thing, basically. So if you look at the y value associated with a, if it's smaller than all the other y values for every other x in the interval, then you call it the absolute minimum. And if it's bigger than all the other y values, you call it the absolute maximum. So let's just see what this looks like in a couple of graphs. So you might try and just pause the video and answer this yourself, but we're going to look at these, and we're going to be considering the open interval from a to b on all of these. So we've got these graphs in green, blue, and red, and we're going to consider the open interval from a to b. And we're going to try and identify a max and a min. Keep in mind that there may not exist. There may not be a max or a min. We don't know when these things occur and when they don't yet. So go ahead and pause if you want to and think about when these happen. Okay, so let's look at the green one. Absolute max. That means we want a y value that's bigger than every other y value sort of within this spread from a to b. So it looks like maybe the biggest y value is 3, but that's an open circle, right? Which means that that point's not actually filled in. So we never actually hit 3. Okay, so that's not going to be the maximum. Okay, but then the open circle also means that 3 is the only thing missing. So for example, there is something that hits 2.99 and something that hits 2.999 and something that hits 2.99999, and we can play that game as much as we want. So that means that there is no max on this interval. Okay, well, what about a minimum? Again, we're thinking about the open interval from a to b. And so here it looks like the interval, like the minimum should be 1. Excuse me. And if you think 1, that's a reasonable thing to think, but it turns out that that's not actually true because we're not including the 1, right? This is an open interval, so we're not including the endpoint a, which means we're also not including the y value of 1, and so we run into the same issue here that we did up here. 1's not included, but there's 1.01, for example, or 1.001, or 1.0000001, and we can sort of get really close to this without ever actually hitting it. So it turns out that there's not a minimum here either. Okay, so let's look at this one that sort of lives between these asymptotes. If you think about the behavior of this graph, right, so this is sort of like approaching this vertical asymptote, and this is going down on this asymptote. So is there a maximum on this interval? Again, you might pause and ask yourself, max and min. It turns out in this case also there's neither, right? There's no max, there's no min, because this is sort of shooting off up to infinity. This is shooting down to negative infinity, so there's no maximum, there's no minimum. You can always get a little bigger for positive infinity or a little smaller for negative infinity. Okay, well, what about something like this? So again, you might pause and ask yourself. So now if we think about the maximum, here we can see that 4 gets hit in our interval, right? And this genuinely does get hit, and it's the biggest thing around, right? So here the maximum is 4, and note that it's the y value we care about. Okay, this is where the minimum or the maximum occurs, but this is the actual maximum. And similarly, if you think about a minimum, right, the bottom of this thing looks like it's about 2, and that's the smallest thing around. So this one does have both a max and a min. It's also possible that you have one but not the other. Okay, we didn't have a graph like that, but I'm just sort of pointing out what absolute max and min is supposed to mean. Well, where did we run into trouble? We ran into trouble, of course, if we had asymptotes like this where you're sort of approaching an infinity, but this didn't have that. This is sort of like an obvious piece of trouble. This is a sort of less obvious piece of trouble, and there are two things going on. The max was prevented because we had a discontinuity in the graph, right? So this is what's called a removable discontinuity. So maybe discontinuity is bad if you're thinking about maxes and mins. The other thing is, this wasn't even discontinuous, but there was something else that was bad, and that is that we weren't including the endpoint, right? If we had included the endpoint, then the minimum would have been 1. And it turns out that those are sort of two defining characteristics for guaranteeing the existence of maximums and mins. So there's a theorem called the extreme value theorem, which states if f is continuous and you're dealing with a closed interval, then there's definitely a maximum and a minimum. Okay, so there may or may not be a maximum or minimum if one of these conditions fails, but these are enough to guarantee that you have a maximum and a minimum. Okay, so if your function is continuous and you're dealing with a closed interval, then you definitely have a max and a min. So again, if you go back up here, we were only dealing with open intervals. This one happened to have a maximum and a minimum, but these didn't have any of them. This one violated both. We were dealing with an open interval and it was discontinuous. This one is continuous, but we were dealing with an open interval. Okay, so that's some information about absolute maxims and mins. Let's talk a little bit about local maxes and mins. This is a very similar idea, except it's one small twist. So a value c in the domain of f, you call the y value a local minimum if there's an open interval I containing c such that the y value is the smallest one around. Or you call it a local maximum if there's an open interval that contains your point such that it's the largest y value. So let's just look at what that looks like. Yeah, so one comment here is that absolute maxes and mins deal with closed intervals, right? That's sort of what you want in terms of guaranteeing the existence, a max or a min. But the definition of local maxes and mins relies on open intervals, right? So like if you go up here and look, there is an open interval. There is an open interval. The other thing about local versus absolute is most of the time for absolute, you're just sort of given an interval and you're asked about it. For local maxes and mins, this is like an existence comment, right? Like if there is an open interval, like you're not going to be given this interval, but just if there exists any interval that satisfies this, then it's called a minimum. Okay, so let's also look at a graph for this situation and see if we can identify some local maxes or some local mins. Okay, so again, you might want to pause and try and think about this if you want. The first comment I would like to make about this is if you consider this function on its entire domain, there's not going to be a max or a min absolute, right? An absolute max there won't be because this is going to shoot off to infinity, so there's not going to be a sort of biggest number. This is going to go down to negative infinity. There's not going to be a smallest number if, for example, we consider the absolute max and the absolute min on the whole real numbers. But that doesn't mean that there won't be local maxes and mins. So in particular, you can see this point, right? If I think about this y value, it's the sort of lowest y value out of all the y values around it. So for example, maybe this a1, b1, that's my open interval. And in this open interval, this is the lowest one around, right? So that means that this y value, we'll call it y1, right? y1 is a local min, right? Because I could find this open interval where this is the smallest y value locally. Excuse me. And again, this is sort of local phenomena. I don't care what's happening in the graph. Or all of the graph. I just need to know what's happening on some open interval. And this interval could be tiny. I mean, like we could also just take some little teeny tiny one here. So similarly, if I go to the sort of top of this next hill, I can find an open interval. Let's say a2, b2, and then let's say the y value here is y2. Well, this is going to be an absolute max because it's the biggest y value around just on its sort of local part of the graph, right? It's sort of bigger than all the people that are directly around it. Okay, so y2 is a local max. And you can see similarly here, right? Like this is going to be a local min, right? Because it's the smallest. I'm just going to sort of write min. And up here, this is going to be a max as well, max. So like the bottoms of hills and the tops, or the bottoms of valleys, right? And the tops of hills represent what are our local mins and maxes. Because if you want it to be the biggest thing around, right? It needs to be sort of coming up and then going down. And if you want it to be the smallest thing around, it needs to be calming down and then start turning back up. So this is what local maxes and mins look like. And again, local maxes and mins rely on open intervals. The definition of absolute doesn't rely on any kind of interval, but if you want to guarantee that they exist, you're going to need closed intervals. Okay, and I want to make an observation here, and I don't have this written yet because I want you to think about it. So you might pause for a second after you hear this question and ask, what is happening where local maxes and mins occur? Right? Can you describe something that uses the language of calculus that would identify where local and maxes and mins occur? Like, what do all of these 4 black dots have in common? So you might pause and try to answer that. It turns out that what they have in common is all their tangent lines have a feature, right, in common, which is that all their tangent lines are horizontal. Okay, so the observation here is that the tangent lines are horizontal at local maxes and mins. Now, it's possible also that the tangent lines don't exist for maxes and mins, which can happen something, I mean, you know, if you've got, maybe you've got a situation like this, and I consider this open interval. Well, this is the smallest y value around, right? So it's also possible that your tangent lines don't exist there. But if you've got a continuous piece of function, your tangent lines are horizontal. But it's also possible that you have a sort of tangent line that doesn't exist because you've got a discontinuity, which wasn't pictured in this graph, but is also possible. So it turns out that places where the tangent line is horizontal, or places where the sort of derivative is undefined, those have a special name, which we'll get to in the next video. So this was all about maxes and mins, what they look like, how to recognize them, a little bit of sort of comparing the differences between local versus absolute.